All right, so welcome to another exciting day here at Spain Park Advanced Level Chemistry. All right, today's going to be a strong day. We're going to get through a lot of stuff today. Start in on stoichiometry, spend Monday, Tuesday, making sure we know how to do stoichiometry. So for those of you here, I just gave you that worksheet that has a bunch of problems on it that we'll go through as examples. For those of you at home, I have posted them in Classroom. So, before we get to the stoichiometry part, I need to just kind of finish up just a couple other little tidbits of information. This is left over from yesterday. So again, this is Graham's law, and what is diffusion again?
The natural spreading out of a substance through another.
Okay, you read really well. The natural spreading out of a substance through another. Okay? And then what is effusion?
Escape of a
through a tiny opening, kind of like helium escaping out of a balloon, the latex balloon. Okay? So, it's real obvious from a qualitative point of view. The bigger the molecule, the slower it's going to go. The harder it is to get through a small opening. Okay? Now, Graham went through and did mathematically, and I showed you the proof, and we ended up with this being Graham's law right here. So what is the rate of diffusion and effusion really dependent upon? The molar mass of the gas. Technically, it's inversely proportional to the square root of the molar mass, but we can really just kind of look at molar mass. This just kind of tells us how fast, and we did the example of nitrogen and hydrogen. And so nitrogen, is 14 times heavier, okay? But when you actually look at the rate, the hydrogen only goes 3.7 times faster because it's proportional to the square root of the molar mass. But it's really just, the bigger the mass, the slower the molecule. So that's Graham's law. All right, so we got another simple law. It's called Dalton's law of partial pressures. What's making up the air in this room?
Oxygen and other gases.
Oxygen and other gases. What are the other gases?
Nitrogen.
The three main ones. 78% nitrogen, 21% oxygen, and about 0.93% not CO2, it's not helium. Helium's actually too light, it escapes. If you pop a balloon, the helium actually goes up, 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 and it escapes out of the atmosphere because gravity can't hold it.
Chlorine.
Nope. You guys aren't even close.
Argon.
Argon. So that leaves how much left? 0.07. Of that 0.07, 0.04% approximately is the CO2. The rest is a mixture of a whole bunch of different things.
Why do we say we have such a CO2 problem if it's only 0.04%?
Because that little bit has the effect. Okay? But you have to realize that when Mount St. Helens and different volcanoes erupt, they put all kinds of CO2 and get greenhouse gases into the atmosphere. And so there's all kinds of stuff causing that. Now, rain tends to wash it out some, and there's a balance. Okay? We just need to plant more trees because the trees use the CO2. Okay? So let me ask you this. So then what causes pressure?
collisions.
With
The container wall.
the container wall. What's causing air pressure on you right now?
Collisions.
Collisions of the air molecules with your skin, right? It's just the weight of all the air molecules, but they're hitting you with a certain force. They're putting pressure on you right now, 14.7 pounds per square inch. Which one's hitting you more? Why? There's more of them, right? So of the 1 atmosphere of pressure, what part do you think is due to nitrogen?
78%.
78%, or 0.78 atmospheres, right? 21% is going to be due to oxygen, because it's number of collisions. Obviously, the more of one type of gas you have than the other, that's going to collide with you more, and so it's going to exert greater percentage of the pressure. That's all Dalton's law says. Dalton's law of partial pressures simply states that in a mixture of gases, the total pressure is the sum of the individual partial pressures. Now don't let that term partial pressure mess you up. That's just the pressure exerted by the nitrogen, that's the pressure exerted by the oxygen. The nitrogen is going to exert and collide with you whether the oxygen is there or not. Oxygen is going to collide with you whether the nitrogen is there or not. So they're all just colliding with you, independent of all the other ones. And so the total pressure is going to equal the pressure of gas 1 plus pressure of gas 2, pressure of gas 3.
Is that a T underneath?
That's a T for total. Okay? So, if I have a mixture of 3 gases, and I have 6 moles of A, I have 3 moles of B, and I have 1 mole of C. And I have the total pressure is equal to 1.5 atmospheres. What's the pressure of A going to be? Think about it like over here. You guys knew it right off the bat right here. How many moles total do we have?
10.
How much are A?
60%.
So 60% of 1.5. So it's going to be 6 over 10 times 1.5. So that's going to be 9.9 atmospheres. So what's B going to be?
30%.
Pressure of B is going to equal
425.
3 over 10 times 1.5 is equal to how much?
4.5%. So
0.45 atmospheres. Notice we have half the number of moles, we got half the pressure. Obviously the rest of it is this, but we can do 1 divided by 10 times 1.5 is it going to equal what? 0.15. Okay? So what we're seeing here is this is called the mole fraction. The mole fraction is, and we've used, for, I don't know where it comes from, just use a capital X, a big X. It's equal to moles of gas over total moles okay, that's what 6 out of 10 is the mole fraction, so 0.6, 0.3, 0.1, that's the mole fraction. It's just however many moles of the one thing in a mixture, how many moles of the one thing compared to the total moles of everything. Okay? Now, what we're doing right here, this is actually known as Raoult's law. Now, you don't have to know this. This is a freebie. Raoult's law says the partial pressure of a gas A is equal to the mole fraction of A times the total pressure. That's what we did right here. The partial pressure of A, the pressure exerted by A, is the mole fraction of A times the total pressure. It's just the percentage. Okay? So don't make that hard. It's just whatever percent is A, it's that percent of the total pressure. Let me say it differently. Whatever percent of A makes up the mixture, that's the percent of the total pressure. Now the most common time we need this, the most practical time we need this, is we're probably going to do a lab after the test. We'll probably do a lab on Friday of next week. Okay? And we're going to make a gas and we're going to collect it by water displacement. So if we collect a gas by water displacement, we can do the chemical reaction of say Mg plus HCl. What's that going to make?
MgCl2 and then H2.
Which is going to be aqueous. It's going to stay in solution. We're going to get H2 gas. So we're going to get bubbles of hydrogen gas. But I need to collect it. I want to collect a volume. I want to know how much I'm actually getting. So I'm going to hook this up to some water. And I can have what's called a gas collecting tube inside of this. And so I'm going to hook up this and so the hydrogen is just going to bubble, 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 double bubble, 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 bubble. And then this is full of water. But what's going to happen as the gas bubbles up into it? It's going to go to the top, and what's going to happen to the water? It's going to get pushed out, right? So the bubbles start coming up, and the purple starts going down. And then if we collected it right there, we could then measure the volume of the gas that's given off. Okay? But when we collect something by water displacement, yeah, we're getting just hydrogen up there, but we're also getting some water. Water's evaporating because water just naturally evaporates. So up in this gas, even though we're really just producing hydrogen gas, because we're collecting it by water displacement, there's some water up there also. So when we measure the pressure inside of here, it's not due just to the hydrogen gas. The total pressure is going to equal the pressure of the hydrogen plus the pressure of the H2O. Okay? So you're always going to subtract this out. Now, if you go to your textbook and you go to the back somewhere, you go to page R79. R79. I'll turn you to it so quickly. Okay. Friday, baby. Come on, let's finish strong. Playing games on your calculator.
You said 79?
R79 is the green.
I was just clicking.
Green pages at the end. At some point, this is going to come on. Here we go. And what we have is a table of water vapor pressures at any given temperature. Because we know, we already learned, that is if you increase the temperature, you increase the rate of evaporation. Right? So that vapor pressure is dependent upon how many water molecules are above how many water molecules are above the liquid? Well, obviously, the more it evaporates, the more water molecules. More water molecules means more collisions, means more pressure. Okay? So the vapor pressure of water is pretty constant based upon temperature. If it's at 20 degrees, it's going to evaporate at a certain rate. If it's at 50 degrees, it's going to evaporate at an even faster rate. So we have the vapor pressures given, now they're given in kPa's and millimeters of mercury. We'll use millimeters of mercury. So you just have to subtract that out. Now, good news is that's always given to you. What you always just have to pay attention to, if it ever says that a gas is collected by water displacement, you have to subtract out the water vapor to get the pressure of what the dry gas. Because the total pressure is going to be the sum of the gas plus the water. We want just the pressure of the gas. All right, that's Dalton's law. The total pressure is the sum of the pressures exerted by each individual gas. The most common time we use that is when we collect a gas by water displacement, which is the most common way to collect a gas and be able to measure the volume. You just either given this in the problem, or you go and you look this up on the table and you just subtract out water vapor. We all good with that? Not too hard? Dalton's law of partial pressures, and then Raoult's law using the mole fractions. Good stuff. All right. Again, that's always going to be given to you. Ooh, we got 30 minutes.
We've only been here for 15.
20.
Hey, that's almost
20's
halfway.
gone by already. What are you talking about?
Yeah. Study more.
Oh man, you got a blank and that class is gonna be over.
I'm going home after this class. I got a reading quiz.
Friday should have been.
Definitely skipping school.
Fridays are the best at 3:35 or 4 o'clock once you get home and I can take a nap. All right.
This is a math assignment, that's due at 11
I
a.m.
was thinking the word.
According to my French speaking assessment, or Spanish.
Gases and our favorite word, stoichiometry.
Yay.
Oh,
I thought we were done with that.
We're never done. All right. There are
Oh,
3
he's
types.
building. He better not be going outside. He's building.
3 types of gas stoichiometry problems.
There's a few things I remember from a while ago in this class, but one thing I'll never forget is you never won't do it again.
You never what?
You never won't do it again.
All right, so the first type is a gas volume to gas volume problem. In other words, you're given 10 liters of a gas and you want to know how many liters of another gas that is made. Okay? So we could say and we'll just even say H2 gas is burned and it combines with oxygen gas, and because you're burning it, you're going to make water vapor. So water gas, and we balance that with a 2 and a 2. Now this is Avogadro's principle. Who remembers what Avogadro's principle said?
equal volumes of gases at the same temperature and pressure contain equal numbers of molecules.
So what does that mean? If I have 10 liters, if I have 10 liters of oxygen, how many liters of hydrogen am I going to need to combine with it? 20. And how many liters of water vapor can I expect to make? No.
We got
2 plus 1 makes,
3.
no. 2 plus 1 makes
3,
2.
2.
What? Oh.
2 moles and 1 mole. Again, moles are just
This is
numbers,
the
but
issue.
this is going to be a bigger molecule. But 2 of these, so we're going to have hydrogen and hydrogen. Going to combine with
Yeah.
oxygen and oxygen, and it's going to make.
At least that makes us feel better when we do bad. That's because 2 plus 1.
Yeah, well, this is new math. This is, what do they call it? The new that everybody doesn't like, Common Core. Or,
That's like saying 2 equals 1.
So 2 hydrogens are going to combine with 1 oxygen. The oxygen's going to go there. The oxygen's going to go there. And we're going to be able to make 2 waters. Right?
Yeah. I have 3
What's
liters.
2 plus 2?
We don't have enough to make 3 waters.
Well, we thought you were like talking about using like 2 in 1.
Well, but the whole point is this, is that
You're like 2.
2 moles combine with 1 mole to make 2 moles. Since volumes contain the same number of molecules, they're going to combine in the same ratio. So that way we can say that 10 liters is going to combine with 20 liters. So how many liters of water should be made? 20.
Yay.
Are you sure?
I'm sure that you guys are the ones that are saying 3. Okay?
2 plus 1 is 3.
With gas volume problems, it's just the mole to mole. Volumes and moles are proportional to one another, so they react in the same ratio. So if I need another gas reaction.
Salmon will have a fit right now.
Why can't I think of a gas reaction, all gas reactions?
Staple that next one right to your hands. Mr. Hobbs, you walked around with a sheet of paper, stapled things. And he's just sitting there, he's like, in case you need it handy, and he just stapled
I was wanting to grab it and he took it off and stapled it again. Okay, wait, no, I should have grabbed the stapler and stapled it to my backpack.
I should have been like,
That's
"Can
all.
you borrow that?" He probably would have been.
Take my paper.
Today is the first day I think he's been out.
Yeah. I know, yeah. He was
Ah.
gone. No,
Okay.
that was the first day, I think. Oh wait, he was there for you? Yes. He was there for their class.
Oh, you missed first.
Second.
Second.
Yeah, no, but he was like the teacher with the sub or whatever, the one we went to the
She was
teacher's
the
class.
ultimate character.
All right, so let's balance this equation.
You gotta put a 2 on the into O5.
Okay?
Put a 5 in front of the O2. Put a
Let's
2
get
in front
it
of the
down.
N2.
And a 2 there, right?
I can do this.
Okay?
Sam, let's right.
So,
Okay, so.
how many liters of N2O5 can be produced from, let's say, 2 liters of oxygen gas reacting with excess N2 gas. Now, this problem sounds way worse, way harder than it is. Just like any other stoichiometry problem, the first thing you're gonna do is you're gonna balance the equation. Second, you're gonna start with what am I given, what am I looking for? Well, I'm given 2 liters of this, and I'm looking for how many liters of that. Because if you don't know what you're looking for, you'll probably never find it. Deep on a Friday.
I'm surprised I pronounced that word correctly.
What word?
Philosophical?
Oh.
I thought for sure I was gonna like stutter.
All right, so what's my mole ratio between the oxygen and the N2O5? 5 to 2 or 2 to 5, right? So that's all I need for this. This is in our stoichiometry roadmap. Mass, the moles, moles, the mass is just the moles part, because volumes and moles react in the same ratios. So I start with 2 liters of oxygen, but now I just have to say, well, I'm going to get 2 moles of N2O5, or you can say liters, it doesn't matter what you put, for every 5 moles of O2. So it's 4 divided by 5,
Which is 0.8.
I'm going to get 0.8 liters N2O5. That's all there is to it.
Couldn't you do it like,
That was it.
couldn't you do it where like, so 5 times 2 is 10, and you divide the 2 by 10, it's 0.2?
Yeah, and I almost did 10 liters. If I did 10 liters, that's times 2, so how many of this is going to make?
Oh wait, that was,
If I use 10 instead of 2.
One more, 4 liters.
Well, 5 times 2 is 10, so 2 times 2 is
4.
4. You guys did that without a calculator. I'm impressed. Okay? So gases is just going to be whatever the ratio is. That's what the gases are going to combine into. The mole ratio and volume ratios are exactly the same. So these gas volume to gas volume problems are the simplest of all.
Let's do a whole bunch of those on the test.
Those will be in multiple choice.
Of course.
Okay?
Well, that's not,
No, that's the hard part.
All right.
You start doubting
So-
yourself.
The second type of problem. The second type of problem. Mass to gas volume at STP. Now we can go either way. We can go mass to gas volume at STP, or we say gas volume at STP and have to find the mass. Okay, so now let's look at the worksheet that I just gave to you. Turn to the side that says molar volume. So I'm going to have to move this over here, and we'll just look at number 1 right here, which is the second number 1. It's the number 1 in the middle. Now, what do we know? 1 mole of any gas at STP occupies what volume? 22.4, right? So we know that the molar volume at STP is equal to always 22.4 liters per mole. So what does that make that a conversion factor between? If you have 22.4 liters per mole, what is that a conversion factor between? What 2 units? Liters and moles. So it's a way to get a gas volume at STP 2 moles, right? So I'm given 600 milliliters of hydrogen gas is produced through a replacement reaction involving solid iron and sulfuric acid. So the first thing that I need to do is write a balanced equation. Solid iron. Does anybody remember what sulfuric acid is? Sulfuric.
it's sulfate.
Sulfate.
plus hydrogen.
So you come here, sulfate is SO4 minus 2.
So 2 H2SO4.
H2SO4. That's going to make, we do have an exam coming up here in a couple of weeks.
Iron sulfate.
SO4.
Okay, we'll say iron 2, SO4, because it makes it easier.
Plus
Okay.
H2.
Wait, is there really no way we can exempt your exam?
Nope.
People last year.
Oh.
We didn't have exams last year.
No,
We
I
were at
meant like-
home.
I meant like the people like that were supposed to, couldn't they, weren't they allowed to last year?
Not as a sophomore, I don't think. I think based upon what you do on, not the PSAT or some test, one of the tests you have to take, maybe the pre-ACT, I don't know if you score high enough, you get out of a math or an English exam or something.
Well, English was, yeah, with Global Scholar. but-
Global Scholar, that's the one I was thinking about. I think English is Global Scholar, math Global Scholar as well.
You can't
Right
get
now,
out.
we
Can't get out of math.
Not this
Okay,
year.
anyway, doesn't matter. Here we go, let's look at this. Okay, so here's my balanced equation. It's nice and easy. It's all 1 to 1 to 1 to 1 to 1.
That's great.
Okay, what am I given? I'm given 600 milliliters of hydrogen gas, and it's at STP. That's important. The question is, how, oh shoot, it does say, let's make it iron 3 sulfate.
I said we just cross
I
out
said,
the
well, we
last.
already wrote it down, you wasted
Iron 3, so what's the formula of iron 3?
Oh.
What's the formula of iron 3?
Fe2SO4.
I can't think right now.
Okay, so now that means I have to put a 3 here, a 2 here, and a 3 there.
Gosh. This is why you don't read the instructions.
What?
Yeah, that's why you just, ignorance is bliss and you just get it wrong. All right, so 600 milliliters at STP, how many grams of iron 3 sulfate, okay, are produced? So this is my unknown. So, you might want to get out, remember that I gave you that stoichiometry roadmap?
Along the same.
Yeah. Why did it go small? Oh, it's just because the thing is small. Okay. So where are we starting on this now? What are we given?
600 milliliters.
Which is a volume at STP, right? First step is always to convert to moles, then to moles, and then we're looking for grams, so we're going to go here. So I'm always going to start with 600 milliliters, but I know that 1 mole of any gas at STP is 22.4, right? So how many liters is that going to be? 0.6, so we did that well in our head. Liters of hydrogen, okay? And I'm starting to go do this way. So what would I put as my conversion factor then to get the moles?
22.4.
And where should it go? On the bottom. 1 mole, 22.4 liters. See, this is actually easier because when you did mass, you'd have to calculate the molar mass. But all gases occupy 22.4, so liters to moles is always 22.4, but only at STP. So now, I'm to moles of known. So how do I get to moles of unknown? The iron 3 sulfate.
The ratio.
The ratio. And from our balanced equation, the ratio,
3 to
okay? Oh, it's right here in front. It's right. It is 3 to 1 or 1 to 3. I always have what I'm looking for on top. I have liters here. I need moles of hydrogen, so moles of hydrogen go on the bottom. So it's going to be 1 mole Fe2SO4 3 for every 3 moles of hydrogen. Now how do I go to grams? Molar mass. Okay. I see several people with calculators out. Somebody type all these in. 55.8 times 2 plus 96.3 plus, can anybody do 12 times 16, 192.
How do you have that memorized?
I just have the 16. I did 16 times 12 is what I just did in
No,
my head.
I'm saying like the whole, like you know all of it.
399.9.
How much?
Did y'all get that? 399.9.
Yeah.
399.9?
Oh yeah.
Good job.
Okay, so now multiply all that out. So 3.57 grams of Fe2SO43 can be expected to be made at the same time as 600 milliliters of hydrogen gas if it's collected at STP. What's the only thing that's different than any of the other stoichiometry problems we've done?
The leader part.
Just using that as my conversion factor instead of molar mass.
Will a lot of them be at SCP?
Well, I mean, we have, the third type is not at STP. It's
So 33%.
So yeah, so I mean, but the gas volume to gas volume, it doesn't matter what conditions you're at, as long as they're the same. And usually when you're doing a chemical reaction, they're all the same conditions inside the container. And so you don't have to worry about, you know, STP or not at STP with gas volume to gas volume. is just the moles to moles aspect. It's just what am I given? Am I given the volume at STP or am I given it not at STP? Okay? So, let's look at another one, just because these are fun. Oh.
I think we should use the road now. Me too. Yeah.
All right, so now let's look at number 2. 14.7 grams of sulfuric acid were used in the above reaction. How many liters of hydrogen could be collected then? Okay, so we have the same reaction, but this time we have 14.7 grams of sulfuric acid. We want to know now how many liters of hydrogen, X liters, at STP. And that, again, as soon as you see STP, 22.4 starts ringing in your head. 22.4 STP. STP 22.4. Pavlovian response. You know, you've heard of Pavlov's dogs, right?
What?
Pavlov taught his dog that, you know, that every time he rang a bell, he gave the dog some meat. And so he would get the Pavlovian response to ring the bell, the dog would start drooling, okay, because he associated the bell with meat. Okay? It's a Pavlovian response. You associate one thing with another. I associate any meal with dessert. Okay? That's how I keep my figures. Now I work hard. I do a lot, so I got to make sure I eat a lot. Okay. So 14.7 grams. So this time, where am I starting on my roadmap? No, I'm not.
The mass for the.
Oh, I thought it said liters.
I have 14.7, so now I'm starting here,
He needs a molar mass.
but I'm trying to get to the volume of gas at STP. Right? So, start with what's given. 14.7 grams of sulfuric acid. How do I convert that to moles? By the molar mass, 98.1 grams.
Okay.
Okay, so now I have moles of sulfuric acid. Everybody knows how to get molar mass, right? You're going to go 2 times 1.01 plus 1 times 32 plus 16 times 4. Okay, that's all the numbers from the periodic table. Okay, so now what? What's the ratio? 3 to 3. Right now, I know it's moot to put that because that's 1, but I always include it just so we don't forget. Plus, it helps with units. So I'm going to say 3 moles of hydrogen for every 3 moles H2SO4. Again, it's always what you're looking for over what's given. We want moles of H2SO4 to cancel, so it needs to be on the bottom. So now how do I take moles of hydrogen to liters of hydrogen at STP? 22.4. So that's the only thing that's different. I have just a different conversion factor. So is that helping you kind of see where, you know, the roadmap, so to speak, where you start, where you're going? They're all the same type problems. You always have to take the given to moles. We just have different conversion factors to do that, depending on what the given is. And what does all this equal? 3.36 liters of hydrogen at STP. Okay? Now you got 5 more problems that are really identical to all this. You're either going to be given a mass and find a volume, you're going to be given a volume at STP and have to find a mass.
I don't know why, but this feels easier than the last.
Yeah,
Because y'all, your brain, as much as you hate to admit it, some of y'all consciously are thinking about chemistry, okay, as you go through life. But everybody's subconscious is taking everything that you're learning and you're organizing it and you're developing it and your brain is constantly working with it. And so when we come back to it, it just makes more sense the second time.
If I paid attention in psychology, I would have known that.
All right, let's look at the last one then, okay? Not an STP. This is the most challenging problem, but I heard somebody say you're gonna have to use what? That's right, we're gonna use, the ideal gas law is gonna have to be our conversion factor between them. Okay? Now, I don't want, there's only 2 problems on there, on the sheet that are like this. Okay, so I don't want to use those 2. I want you guys to have practice, be able to practice those on your own. So I'll make one up. How many liters of oxygen gas collected at 25 degrees Celsius and 750 millimeters of mercury and this is going to be not very grammatically correct, but can be formed when 15 grams of KClO3 is decomposed. And this is the reaction we did to get the percent oxygen in KClO3. We did this lab. We heated this up, decomposed it. The oxygen just went off. We did not collect it, but we could have collected it. Does anybody remember the equation with KClO3? We heated it up. What's it going to decompose into? KCl, the white solid that stayed in the crucible, plus oxygen gas. We balance it with a 2, 2, and a 3. Now, so there's step 1, write a balanced equation. Step 2, what am I given? What am I looking for? I'm given 15 grams of this. Now I'm looking for how many liters, but it's not an STP. So I go ahead and I'm going to say temperature is equal to 25 degrees Celsius and the pressure is equal to 750 millimeters of mercury. So where am I starting now and where am I going to? I'm starting in grams, right? But I have to go to a gas volume, not at STP. So I'm going to take grams to moles. How do I take grams to moles? Molar mass. Moles to moles with the coefficients. But then instead of being able to just plug in, now I'm going to have to use V is equal to nRT over P. Okay? So N is what unit? Moles. So I just need to stop at moles and then plug it in. I'm not going to go to grams. There's no need to go to grams here of oxygen because N is moles. You go to grams, you're just going to divide by the molar mass again and go back to moles. Okay? So we start with 15. You have to do this in 2 steps. You can't do it all in one big old long step like we did all the other problems. This is the only stoichiometry problem that takes 2 steps. You can't put it all into one. Ooh, getting excited. 15 grams KClO3 times 1 mole over 122, but I think it's 122 point something. Okay, somebody type them in. 48 plus 35.45 plus 39.08.
122.50.
122.53. Okay, so that's just like normal, grams to moles. What's my mole ratio? What over what? It's 2 to 3, but what goes on top?
3.
3. Okay? Now this case we need to stop because we need moles is what we need. We don't need, for PV equals nRT, we need moles, not grams. So we don't have to do that last step. This comes out to how many moles?
0.184.
Do we agree with that number? Is that my answer? Is that my final answer? Yeah. So now I have to use the ideal gas law to solve for volume. So volume is equal to nRT over P. So N we just calculated, 184. R is always 0.0821. Temperature has to be in what unit? So it's 298. And what unit does pressure have to be in? How do we get to pressure to atmosphere?
760.
0.97?
I got 0.99. Because when you do 750 over, yeah.
Over 0.99?
Wouldn't it be more accurate just to put divided by 750 over 750?
You can if you want to. You can just put that in as one thing. I just trying to not make it more, trying to make it less complicated by just doing it separately. But yes, you could have just plugged this in 750 over 760 down here in the denominator. And as long as you use parentheses, your calculator can do multiple levels of parentheses. So what does all this come out to?
4.56 liters.
Liters of oxygen. Okay? Now, we used between 1.5 and 2 grams. So what do you, how many liters of oxygen do you think we made? We used 1.5, 0.456 liters. Okay, about a half a liter of oxygen got produced, and we breathed it all in and felt good.
How many ounces is a liter?
Well, how many ounces in a liter? There's 16 ounces in a pint, 2 pints in a quart, so 32 ounces in a quart, and a quart is a little bit smaller than a liter. So I'd say 34